So here we go. So I'm going to pick the color of the day. I've been going with this green. I'm going to go with this light blue. Random question time. If you guys are watching this either really late on Thursday or some point on Friday or the weekend, I mentioned before, Minithon is coming up. They're doing some fundraising starting this Monday, and I am teamed with Mr. McDaniels, and we're looking for some ideas to raise some money. So our goal right now, I think, is about $200. So if we can raise $200 for Minithon, we will do something crazy. I don't know what ideas we've been discussing via text back and forth, or do something kind of fun for you guys as far as like, I don't know, extra credit or something. But typically all of our students are pretty well off grade wise, and we want to do something that would be fun for you guys. So if you have any ideas, feel free to send me a message. All right, so number 5, let me get to my book here. So we have 2 springs that are identical, except that spring 1 is stiffer than spring 2. So that means their K values are different. So spring 1, spring 2. K1 is going to be bigger. K2, let's do like a kind of like relative size here. K2 is going to be small. So if we were to look at those springs, the thickness of them usually varies. So this one might be like a medium-sized spring. This one might be like a really thick spring like that. Whoa, that's a little bit much. Maybe something like this. Something that you would see more in a car. So spring 1 might be like associated with the car. Spring 2 maybe like that little spring in a clicky pen. And clicky means like you click it and you can write with it. You click it again and you can't because the pen part comes back. So for part A, if they are stretched using the same force, for which spring is there more work done? So a couple of things we need to discuss. Work technically is force times distance, but work can also be change in energy. So I'm going to kind of get rid of this because I don't like that distance part. I'm going to put delta x, displacement of the spring. So if they're using the same force, we're not really concerned with that aspect of it. It's really how far they're stretched. So if we have these 2 springs, whichever spring has the larger K value, it's not going to stretch as far. So really it's just, the smaller K value is going to grant us that larger displacement. So we can see simply conceptually with work being force times displacement, we have that greater displacement in that smaller K value, giving us our, let's say spring 2 being having our more work done. Because it will stretch further. Part 2, or part B rather, if they are stretched the same distance. So now we're looking at still work being force and displacement, or the change in energy. So they're stretched the same distance, so that means for spring 1, since it was a stronger spring, a higher K value, more force was needed to stretch spring 1. And I'm thinking backwards. I just want to clarify that, for part A, um, there was more work done for spring 2 because it moved further because of the same force. I just remember myself maybe talking in circles a little bit. For part B, they are going the same distance. So more force is needed again to stretch that first spring out. So that means spring 1 rather is more work. If you look in the Giancoli solutions, they go through like a derivation. I think it's a little bit easier just to think in terms of conceptual, but for those math folk that are more algebra based or calc based or pre-calc or however you want to look at it, feel free to look at the Giancoli solutions. Next one was 6. So if the speed of a particle triples, by what factor does its kinetic energy increase? So we're looking at kinetic energy. It's always a good place to start for our equation sheet. And we're just comparing overall energy and velocity. And we see that they're not directly proportional. They're proportional by a square of the velocity. So if for some reason the speed of the particle triples, that overall value is going to be 9 times as big. So it'll have 9 times the overall kinetic energy. And this is important with driving cars. Most people think you go from 25 miles per hour to 50 miles per hour. You have twice the energy. You only need twice the amount of distance to stop. But you actually need, when you're doubling your velocity, 4 times because your velocity is being squared. So your brakes and your tires have to do 4 times the amount of work because of the exponential relationship between velocity and energy, or the change in energy and the work needed to come to a stop. Next question we had, let's make sure it's not 7. Nope, we didn't need 7. We're going to 8. And we have our picture there where we have a box. I'm not going to draw the hand. I'm not really good at drawing. But this is distance D here. And then that other distance D. So this box is going to move a total of 2 of these D distances. So these are positions A, B, and C. And we're also told that at position B, so velocity at A is 0. So at position B, we're calling it VB and then VC. That's basically what that paragraph is telling us in number 8. And it says, when the block has traveled this other distance D to point C, will its speed be greater than, less than, or equal to twice the velocity of B? So we're given that we're applying a constant force. So if we remember back to Newton's second law, whenever there's a force applied, it's going to accelerate. So our object is speeding up faster and faster and faster. So we're looking at this position versus this one. I know I didn't draw the boxes the same. I'm sorry. So we're going to go faster. So at A, we're not moving. At B, we're going some speed, and at C, we're going to go some other speed. But is it twice as fast? Meaning, are we going twice as fast at C as compared to B? So bear with me here. So some concepts here. Work we know is force times distance. We know work is also equal to the change in energy something has. And the energy we're talking about, in this case, is kinetic energy. Well, then how is kinetic energy related Sorry, that's my son's school calling for a virtual day tomorrow. Um, so our change in energy is proportional to the velocity squared. So if we have twice the distance, right, that means we have 2 times the work because it was 2 times that distance. So that also means we have 2 times the total energy or change in energy, right? In the beginning, from just going from A to B, that was one amount of change. Now we're going 2 distances or 2Ds. That's twice that energy. But when we look at velocity, though, it's going to be the square root of that 2 velocity to get that actual number, because this is what we're solving for. So we're thinking we have all these numbers on the left, they're values of 2. So essentially it's going to be a 2 is proportional to v squared. So just v would be the square root of 2. So it's going to be about 1.2 times that via VB, because that's what we're really talking here, or VC is the square root of 2 times that velocity at B, or 1.2 times as much. And again, if you want a more detailed algebraic explanation, be sure to check the Giancoli solutions. I'm going a little bit more conceptual here. So now we're on 9. We'll go back to our color of the day, which I forget. Nine, we're going to lift a heavy book from a table to a high shelf. List the forces on the book during this process and state whether each is conservative or non-conservative. So pretty easy. If you're going to lift a book, if you were going to draw a force diagram for that book, you would have some kind of force applied going up, and force due to gravity going down. So now we need to talk as far as conservative versus non-conservative. Now this just means, is this associated with an energy that we can get back? Are we storing energy? So of these two forces, the only one that is involved in storing energy, like to get this energy back to us, is going to be the gravitational. Because this part here, this mg, this is our force due to gravity. So if we were to say lift this book up on the shelf and for some reason it slides off and hits us in the nose, it can do work on our nose. It can transfer that force back to us and move our nose a certain distance. It changes its position with the force. So as kinetic energy or work, we can look at that. But just us lifting that book up, is that applied force going to do anything? Not necessarily. So this applied force, we can't get back. We lost that energy. So meaning the calories that we burn lifting it up on that shelf, can we get that back as stored fat? No. We're not going to gain weight by letting books hit us in the face. So that's going to be a non-conservative force. And then our force due to gravity would be our conservative, meaning it's stored there to use. Conservative. They also mentioned in the solution air resistance. Usually we're not really concerned when we're putting books up on the shelf with air resistance, but that air resistance, there'll be a minuscule amount of air resistance lifting that up, so there is a little bit of thermal energy associated with that, and that thermal energy, that frictional force would not be conservative either. Moving on to 10. So we have a hill of height h, pretty basic hill. Height h, we have some kind of object, mass m, child on a sled, and they're going to go from the top to the bottom. And we're looking at those two positions. Does the speed at the bottom depend on the angle of the hill? So we're looking at it going from being all gravitational in the beginning to all kinetic in the end. And since there is no friction, this is an icy, hill. There's no friction, which, interesting enough, I don't know if I mentioned this in class, for the first time in, I don't know, how long have I lived in this house? 14 years or so. For the first time ever, there's a steep hill behind my house and like a street, like a road. And kids skateboard down it, bike down it, scooter down it all the time. But for the first time, that first big snowstorm that we had this year, where it was like really icy at the end, I saw kids sledding down this almost 400-meter, like quarter-mile portion of a road because the coefficient of friction was so low. It's just all like a sheet of ice. If it's just like hard-packed snow, it doesn't work. And we were able to ignore the friction and then go from all that gravitational to kinetic. So I thought that was a really interesting experience that I had for the first time, like in 14 years living in this house. So if this is what we're looking at, the steepness of that slope would not matter. So it doesn't matter whether it's, a really steep slope or a really gentle slope. So we could have another picture where we had this extremely steep slope, that same h, and nothing about our situation would change, right? Because at the end of the day, the masses cancel out. Gravity is the same no matter what we do. The height is the same for both cases. And we would solve for the velocity, and it would be the same. Now, when we turn on friction, though, or keep it on, we add another component to our energy equation. And that's going to be thermal energy. We're going to lose some of that gravitational potential energy, meaning it's not going to go right into our motion as kinetic energy, but it's going to cause, there's going to be friction. Our sled is going to heat up a little bit, maybe melt some of the snow as we go down. And the reasoning is because of the angle. So the steeper the angle, meaning the angle with the horizontal. So if this was like 30, and this is maybe, I don't know, this is extreme. I'm just going to put 60. So that 60-degree angle, our component of gravity that's going down our slope is going to get bigger. Well, what is it that determines friction? It's not our component of gravity that goes along our slope. It's the one that is perpendicular to our slope, meaning our normal force. So where our normal force is bigger, say in our first case, if you wanted to sketch a force diagram, feel free to do so. We're going to have more friction, so more energy lost to thermal energy, so we're going to have less for that kinetic energy, less velocity. So that's what friction does. The steeper the slope, the less friction, the faster you will go. Well, the faster you'll go because the force is bigger, but the less energy you're going to lose because of friction. Let's see, we're on 11. 11 is talking about a pendulum. All a pendulum is if you had, a string or a cable attached to a mast that's hanging, and you pull it up and you let it go. It's basically a swing. So imagine the playground swings, but you're not allowed to kick your feet and move your body so that you can go back and forth. It's just like having somebody, if you had like a little kid, like a baby, or toddler, you pull them back and you let them go. That's basically a pendulum. So it says analyze the motion of a simple swinging pendulum in terms of energy. Ignore friction. So part A, no friction. This pendulum would move back and forth. So if we pulled it back to A, it would go to position B, and it would go, let's do some dotted lines, to position C. These angles would be the same. How do you do angles that are same? I guess like that, right? And it would keep on going to those same heights, those same angles back and forth, and would continue moving forever if there were no friction. So that would follow the law of conservation of energy. But the law of conservation of energy is a little bit harder to look at in the real world because we always have friction and we're losing friction. So in our system that we're trying to keep constant and keep all the energy there, it's usually moved around and spread out. I forget the chemistry term. Entropy? Entropy and enthalpy. Entropy is the idea, I think, that energy is always spreading out, if I remember my chemistry terms correctly. B. Now if we have friction. So we're going to have two sources of friction here. One would be probably however this is attached at the beginning. That string is going to be moving back and forth. Whether you tie a knot or a loop, it's going to be moving. Two surfaces come in contact. You're also going to have a significant amount of air resistance. So think, going to, if you've ever had like a little sibling, you're babysitting, niece, nephew, you go to the park and you pull them back on the swing, you let them go, they're eventually going to come to a stop because they don't know how to swing yet. They don't know how to kick their feet and kind of manipulate that situation. So they're slowing down because of friction. And this is why there's things that have to be wound up. If you know what like a grandfather clock is, it's the big thing that has that pendulum that goes back and forth. You have to wind it every once in a while, usually once a month, or it's going to be off as far as time goes. Because it's basically a pendulum. It's a pendulum clock. So there's another little spring inside or coil that you wind up to add that additional little bit of force to compensate for friction. Same thing for non-battery powered watches. This is why you have to wind watches, or the watches that you can, as long as you're moving them, they're kind of charging that battery per se. 14 is the next one we're looking at. I'm going to switch to yellow. 11. So we have experienced hikers prefer to step over a fallen log in their path rather than step on top of it and step down the other side. So think about going up a mountain, right? So here's the ground. You're going up. That's a weird looking mountain, right? You're going up to here. Position A to B. And you're taking your energy, your chemical potential energy. You're doing work to get up to this position where it's all gravitational potential energy. So anything you do to add to the total vertical height is going to take calories. It's going to take work. Other biological things going on in your body while you want to do it, but it's essentially just transferring the energy and the amount of work that you're doing. So kind of zoomed in here. Here we have a side view of our log. And we're here. If we simply just step over this log, we're not lifting our body. We're just lifting our legs. Maybe it was a bad sketch here. A little bit bigger. So we just really need to lift our legs over this log. But if we step up onto it, Sorry, they changed some of the notations here on an update. So if we have to move our whole body up here, we did additional work. Well, if we have to do that 20, 30, 40, 50 times, we're going to be moving more weight upwards. So we're not necessarily getting that energy back. So we mentioned that applied force going upward is not conservative. So we're going to be, at a loss. We'll be really, really tired if we're stepping up and over every single log instead of just stepping over it, putting our foot over it. 16. We're 16. So this is our picture. This is our, if you look closely at this picture, we have to look at what's wrong with it. So we definitely see the waterfall. See figure 6-32. The water's going down, but if we track it backwards to where that water's coming from, the water is actually coming from below it. It doesn't make sense. I mean, you do see that little that water wheel below it, but the waterfall is actually making the water wheel turn. So water doesn't, for at least for long distances like we have here, travel upward. So that's what's physically wrong with it. We have water flowing upward and there's no apparent pump causing it to go up. So that's a little trick. Sometimes you have to kind of squint your eyes and look differently at this picture to see what's really going on. I think we got 2 left here. 17, 2 identical arrows, one with twice the speed as the other. They're fired into a bale of hay. So the hay is used to stop it. And this, we're assuming that like everything is constant friction-wise with the arrows in the hay. The faster arrow will penetrate how much further than the slower arrow. So let's look see what we're doing. It's going to have kinetic energy, and then that energy is transferred to work, which is force times distance. So it's going to be the force of friction, which is the same for both arrows. So we're looking at the relationship between kinetic energy and the distance into that bale of hay. Wait, I'm sorry, twice the speed. So I forgot something. So since this is 1/2 mv squared, since the velocity is squared, we're looking at 2 being squared. So it's not going to be, since it's going twice as fast, it's not going to be going twice as far into that bale of hay. It's going to be going 4 times the distance because of the relationship between the velocity and the distance. I kind of started off a little bit weird with this equation. It's not, if it said twice the energy, just overall energy, then it would be twice the distance. But it says twice the velocity. Because when you have twice the velocity, you have 4 times the energy. So you then can say like, energy and distance are proportional, directly proportional, but it would be 4 and 4. And I think we have one more left. Number 21, suppose you lift a suitcase from the floor to the table. So that's pretty easy. You have a basic table and you have some kind of suitcase, I don't know, with a little hook here. And you're going to lift it. So it's almost like a multiple choice question. The work you do on the suitcase depends on which of the following. So something to consider with work. The force that you apply needs to cause its motion in that distance that it moves. So a push-up is called a push-up because you're only working out on the way up. Physics-wise, you're not doing any work on the way down. Now, I know there's other, biomechanical stuff going on. If you were just to hold a plank or go down in the push-up really slowly, but just physics-wise, you're only doing work on the way up because you're pushing up and you are going up. But on the way down, your force is up and you are going down. It's opposite directions. So let's see. Part A, you lift it straight up or along a more complicated path. So it doesn't matter which way you move it, you're still doing work because we're taking this suitcase, which is this dot, and we're putting it here. So we're using a force to move it that distance. Now, whether we move it straight up or at an angle, that'll change some things. That'll change how that same amount of work is being done. Whether it's more force in a little distance or little force in a big distance, we would have the same amount of work. B, the time the lifting takes, right? We're looking at work. Work is just force times distance. There's no time involved in lifting it, so that would not affect the work. That would affect the power, which power is, work per time or change in energy per time. Part C, the height of the table, that definitely will determine the work because that's going to change the distance. And part D, the weight of the suitcase, that will change the work because it's the force. So it's really I know we're not applying the force due to gravity, but that force due to gravity would be equal to our applied force, our normal force, or tension force, depends on how you look at it. But these are the only two factors that will determine the amount of work done, not the time, the speed that you do it in, so just where it moves and with what force. And we can actually write this a little bit differently if you want. Delta x, or in this case, delta y. And that is your questions from the homework. And keep an eye out tomorrow at some point, probably midday, hopefully, for the misconceptual questions, which that should go really fast, and the problems, probably about the same length as this video.